Hello friends, after discussing the shear strain and the relationship among the three types of velocities during cutting, we are here once again to discuss the merchant's force analysis. Merchant use a circle to show the relationship among the forces, different forces: cutting force, thrust force, normal force, shear force, friction force, and the any other type of force, the resultant force. So we are going to discuss that, and we will find the relationship among the different type of forces. We will find the merchant's relation, which merchant found and used, and also the modified merchant's relation. So there are other relations also, like you have Lee and Schaeffer relationship that will be given to you in the exam, or you must remember this, and Stabler relationship, and so on. Some other relationships are also available. So merchant and Lee and Schaeffer, they are predominantly used. Modified merchant and Lee and Schaeffer. If any other relationship is to be used, that will be indicated in the question in the exam. So here we have this diagram which you are familiar with, and it is worth repeating that if you like this lecture, then please subscribe it and share it. So this is the tool, the job workpiece, moving with a velocity vc in this direction, and the chip is moving in this direction, v chip. Shearing is along the shear plane. So we can assume that chip, which is a lump of the mass, if you consider the equilibrium of this lump of mass, only this portion, it has been sheared here. So this is moving along this. So what are the forces acting on it? The total force acting on it applied by the tool is R. So it is having two components, one is normal and other is friction. Friction is along the surface of the tool, and this is normal perpendicular to it. So R resultant makes an angle lambda, which is the friction angle, with the normal. Now for its equilibrium, an equal and opposite force R dash must be acting on it, and these two must be in same line. The line of action must be same, and R dash equal to minus R. In magnitude they are same. So this is acting here, so it can be resolved. One component is the normal force, normal to the shear plane. Other is Fs, which is along the shear plane. So these forces resolved can be shown with the help of a circle, the diameter of which is the force R or R dash. So let me draw a circle first. This is the diameter, and this shows the force R or R dash. So we can resolve this into two components. One component is the shear force. This is the shear force, Fs, and other component is normal to this. Fn is normal to this. This is the horizontal line, and it makes an angle phi with horizontal. This is the vertical line. Then we have the components F and N, and we can resolve R further into two components, F and N. This is the force F and N. So you can show the direction. F is in this direction and N is in this direction, and F is inclined. This is the vertical line. This angle is alpha. So F is inclined to the vertical at an angle alpha, means this angle is alpha. This is also alpha. So this angle, the opposite angle, is same. Now we can resolve the force R further into two components. One along the direction of cutting velocity, the cutting force, and other is a thrust force acting perpendicular to this. This is the horizontal direction, and in this direction, or the direction of cutting velocity, we have this force Fc, the cutting force, and the component normal to this is thrust force Ft. They are perpendicular to each other. So this angle is phi. So by the rule of sector of circle, this the same segment in a circle will have same angle included. This will also be phi. This is phi. This will also be phi. And r makes an angle lambda with n. This is pi by 2. So this is pi by 2 minus lambda. This is alpha. This is horizontal. This is vertical. This angle is pi by 2 minus alpha. So we get this angle equal to lambda minus alpha, and this is phi. So this whole angle becomes phi plus lambda minus alpha. Now we can write the relationship among the angles, among the forces. You can resolve the forces and find the components. Fc can be written as equal to, Fc I will write in terms of Fs and Fn. Fs cos phi plus Fn sin phi. So Fs is acting in this direction, and this is making an angle phi with this. If you extend this line in this direction, this angle will be phi. So cos phi will be in this direction, sin phi will be in this direction. So taking this direction as positive, or the direction of Fc, Fs is having cos component in this direction, direction of Fc. What about Fn? Fn is this, and this is having a component in this direction and in this direction. This angle is phi, this is 90 degree, this is 90 minus phi. So this is Fn cos 90 minus phi, means sin phi. Both are in same direction, so positive. Then I can write Ft. Fs is having one component in this direction, Ft is in this direction, so this will be negative, and Fn, as I told you, will be having cos component in this direction. So Fn cos phi minus Fs sin phi. Similarly, you can resolve the other forces, and we get F is equal to Fc sin alpha plus Ft cos alpha. You can resolve and check here. Fc cutting force in this direction, Fc sin alpha plus Ft cos alpha, and n is so these you can learn how to find, and then you should remember all these relationships. And we have Fs is equal to Fc cos phi minus Ft sin phi, and Fn is equal to Fc sin phi plus Ft cos phi. Now apart from this, you can write this angle is pi by 2 minus lambda, this is F, this is N. So I can write that cos of pi by 2 minus lambda is equal to F divided by R. Similarly, you can write for N also, and we can also write this angle is lambda minus alpha, this is phi, so this angle, whole angle is phi plus lambda minus alpha. So we can write that Fs is equal to, this force is Fs, R cos phi plus lambda minus alpha, and Fn is r sine phi plus lambda minus alpha. And we can also write the relationship among these two forces with r. Fc is r cos lambda minus alpha and Ft is r sine lambda minus alpha. So the coefficient of friction here, mu is F by N Fc sin alpha plus Ft cos alpha divided by Fc cos alpha minus Ft sin alpha. Sometimes you will find in the question it will be given to you that tool has a zero rake. In that case alpha is 0. So mu will be equal to Ft divided by Fc. These components of the forces, they are measured with the help of a dynamometer. There are different types of dynamometers available for measurement of these forces. Like drilling forces can be measured with different dynamometers, and the forces during milling, grinding, etc., or the turning operation, they are measured with different dynamometers. So these are the relations. And what is the shear area? You can see here, this is the shearing surface. So if I show you the view of the material being sheared, this is the shear plane which is making an angle phi. This is width of cut W, and this is the uncut thickness, this is the chip thickness. So we can find the area which is sheared. So this area is W into T1, and this is the sheared area. Area measured like this in the direction of the shearing plane. So sheared area is W T1 divided by sin phi. This area divided by area along the diagonal. So the ratio is equal to sin phi. So shearing area, or the area which is sheared, is given by this. Suppose the shear stress is tau 0. So the shear force is equal to the shear stress tau s, let me write this, into shearing area. This is the relation that we will be using for finding the merchant's relation. So the cutting force is Fc is r cos lambda minus alpha. Put the value of r from here. Cos phi plus lambda minus alpha into Fs. Fs is W T1 tau s divided by sin phi. So I have used this and this, these two relations, and put the value of r from here, Fs divided by this in this, and Fs I have put from there. So here you can see the work expended during the cutting operation is Fc into Vc. The cutting force multiplied by the cutting velocity. So this is equal to W T1 tau s cos lambda minus alpha into Vc divided by sin phi cos phi plus lambda minus alpha. So here you can see that this is a function of phi only, because if you increase the value of alpha, then you can see phi will increase. from the diagram. Increase means this rake surface moves in this direction. Then this part of the tool, or this angle which is known as the lip angle, this will decrease, but the shear angle will increase in this case. So for a given value of the rake angle and the combination of workpiece and the chip, that is for a given value of lambda, and all other parameters are constant, so work expended during cutting is a function of the rake angle phi only. So we have to optimize this so that the work is minimum. So work is minimum when denominator in this expression is maximum, d by d phi of sin phi cos of phi plus lambda minus alpha. For this to maximize, this must be equal to 0. So we can write cos phi cos of phi plus lambda minus alpha minus sin phi sin phi plus lambda minus alpha equal to 0, or cos A cos B minus sin A sin B, cos A plus B, 2 phi plus lambda minus alpha equal to 0, which is cos pi by 2 in general. So this is the relation which was obtained by Merchant using this analysis. Here lambda is equal to tan inverse of mu. So Merchant used this relation. This is known as Merchant's first relation. So this relation was good as far as when it was used with cutting synthetic plastics, but when it was used for machining the metals, this did not yield proper results. So as a result of this, Merchant investigated into this and found another relation by considering the normal stress during the cutting operation also. So what he did, let us discuss that also, the Merchant's modified relationship. As you can see here, the Fs shear force is acting along the shear plane. So Merchants first analyzed this, and by assuming that the shearing is occurring only because of this force. But here you can see the normal component is also acting on this. So now when Merchant found that this theory yields good results only with non-metal like plastics, then Merchant took into consideration this normal component also, and Merchant assumed that a normal component of the stress, that is normal stress, is also acting during the cutting operation. So this is how he obtained the total stress acting on the shear plane, that is equal to a stress, a component of the shear stress tau S0 plus a constant multiplied by the normal stress sigma n. K1 is a constant here, and sigma n is the normal stress which is acting on the shear plane because of the normal force, and this normal stress Fn divided by the shear area Wt1 divided by sin phi. Now we can write the relationship, and Fn and Fs, if you remember I had written the relations, they are related as tan phi plus lambda minus alpha. So I put the values in this equation. This is Fs divided by Wt1 by sin phi is equal to tau s0. This is the minimum value of the shear stress, a constant value, plus K1 into sigma n Fn, and put the value of Fn from here. This Fn I am putting from this Fs tan of phi minus alpha plus lambda divided by Wt1 upon sin phi. So this gives you Fs is equal to Wt1 tau s naught upon sin phi into 1 minus K1 tan phi plus lambda minus alpha. So this relation merchant used to find the cutting force. Fc was equal to Wt1 tau s0 cos lambda minus alpha upon sin phi cos phi plus lambda minus alpha minus K1 into sine of phi plus lambda minus alpha. And for minimizing the work expended during the cutting operation, the same procedure was repeated to maximize the denominator, and the result obtained was equal to 2 phi plus lambda minus alpha equal to Cm, and Cm is cot inverse K, which is known as the machining constant. This is a constant for the work material. Depends on work material and cutting conditions. So this relationship is known as merchant's modified relationship. This gave good results when the machining was done on the metals also. If you draw the graph between phi and lambda minus alpha for machining a particular material, according to Merchant's theory, the graph must be like this. And for machining mild steel, the graph was like this, parallel to this. This is Merchant theory. According to, the graph must be like this. So for many materials, when the graph was plotted, we got the results which were confirming this is for lead and this is for copper, etc. So different materials, when they were used, metals, they gave the result which was in agreement with the Merchant's modified theory. So this is how the Merchant's force analysis is done, and we arrive at the results. So there are some other relationships also, two of which we have discussed here. Sometimes you may be asked to use some other relationship, and let me write these here. We have by Lee and Schaeffer, that is given by phi plus lambda minus alpha is equal to pi by 4. Then we have Stabler, phi plus lambda minus alpha by 2. this is equal to pi by 4. Sometimes these may be asked to use in the exam. Otherwise you have to use the Merchant's original theory. Sometimes Merchant's modified theory is also used. Generally you will have to use the Merchant theory. So these are some of the theories which were used for obtaining the better result during the cutting operation, which are in agreement with the theoretical results. So apart from this, let me discuss with you the relation between cutting force and chip thickness ratio with cutting velocity. As you know that when cutting velocity increases, the cutting force will decrease. This is the graph of FC, and chip thickness ratio will increase. R is equal to T1 by T2. T1 is uncut thickness and T2 is the chip thickness. So as you increase the speed, the chip thickness, that is T2 will decrease, because if you increase the speed, that means you have to machine a finer mass having less thickness. So this thickness is T2 and this thickness is T1. So as the cutting speed increases, this has to decrease. So R equal to T1 by T2, this increases. Similarly, we have the same relationship of FC and R with the rake angle alpha. If you increase the rake angle, the cutting force will decrease and R will increase. So these two graphs, they are very important, so you should remember these graphs. And now we can solve some questions. Let us solve few numericals from this. So the first question is, during an orthogonal machining operation on mild steel, the results obtained are given as T1 is, and we have T2 is 0.75 mm, width of cut 2.5 mm, rake is 0, the cutting force is measured as 950 Newton, and the thrust force is 475 Newton. So you have to find coefficient of friction between tool and the chip, and apart from that, ultimate shear stress of the work material. These two things we have to find. Now you know that mu is, if you remember the result, F by N, which is equal to Fc sin alpha plus Ft cos alpha and here you have to use alpha equal to 0 degree. Equal to Ft divided by Fc, because alpha is 0. 475 by 950 equal to 0.5. Then the area of shearing, Wt1 by sin phi. So phi we have to find. So tan phi is R cos alpha over 1 minus R sin alpha, and R here is T1 by T2, 0.25 by 0.75, 1 by 3. So this is 1 by 3 cos 0 upon 1 minus 1 by 3 sin 0, 1 by 3. So phi is tan inverse 0.33, and this should be equal to 18.4 degree. And we can also use the merchant theory for this. If you want, you can use, because alpha is given, phi is given. Now the shear area is 2.5.25 upon sine 18.4 degree and 1.99 mm square approximately. So we have, first of all, we have to find the shear force, and Fs is equal to Fc cos phi minus Ft sin phi. So Fc Ft are given 950 into cos of 18.4 minus 475 sine of 18.4 degree. So we find Fs as equal to 751 Newton approximately, and the shear stress is Fs divided by As, 751 upon 1.99. So this is approximately 379.5 Newton per mm square. You can also use the merchant relationship for this and phi using 2 phi plus lambda minus alpha equal to pi by 2. So we have the value of phi, alpha, so you can find lambda and then you can proceed. So this is how you can solve the question. Let us move on to the next question now. So the next question is that mild steel is machined at a cutting speed of 200 meter per minute. Speed for mild steel, you should remember this value. Sometimes this is also asked in the exam. With rake angle equal to 10 degree, width of cut and uncut thickness. W is the width of cut. So this is equal to 2 mm, uncut thickness 0.2 mm. Average value of coefficient of friction is 0.5 and shear stress of the work material is 400 Newton per mm square. You have to find the shear angle, then the cutting and thrust component of the machining forces, Fc, Ft. So these three things you have to find, and here you can use the merchant's solution. Merchant's first theory you can use, it is given in the question. So we have, according to merchant's theory, 2 phi plus lambda minus alpha equal to 90 degree. So lambda is equal to tan inverse mu. If it is given to us, then we can use this theory. Tan inverse 0.5, which is equal to approximately 26.6 degree. So 2 phi plus lambda minus alpha equal to 90. So friends, this gives phi is equal to approximately 36.7 degree. Now we have got the value of phi. So the sheared area is Wt1 by sin phi. So 2 into 0.2 by sine of 36.7 degree mm square. And Fs is As into tau s into 400 Newton. So this is approximately 262.3 Newton. Now you can find the other components. We know that Fs is r cos phi plus lambda minus alpha. So let us find r first. Fs upon cos of phi plus lambda minus alpha. So we get this force R is 438.6 Newton, and you know that Fc and Ft, they are related to R cos phi minus alpha and R sin phi minus alpha. Cos of 36.7 minus 10 degree. So Fc is around 420 Newton and Ft is R sin lambda minus alpha. So this gives you around 125 Newton. So this is how you can solve the question using the merchant's analysis. So apart from this, there are many other questions that we can solve and that we'll be doing in the next discussion. So you should go through this very carefully, because you will get the questions from this part in any of the exam you appear, and also in the interview you will be asked the different types of questions from this. So engineering or GATE or any other type of exam, you will find the questions from this. So this is all for this, and if you